Hello everyone, welcome to the CIB ECR webinar on AI in construction, which is focused on the application areas and implications of using AI in design and delivery of projects. I am Sina Moradi, CIB Program Director and Assistant Professor of Project Management at the Bartlett School of Sustainable Construction, University College London. We have two keynote speakers here today, Dr. Fulvio Cecconi from Polytechnic di Milano and Dr. Ruichuan Zhang from Virginia Tech. So let's now proceed with the first presentation by Dr. Cecconi.
Thank you very much, Sina, and thanks to everybody for joining this webinar. Let me just share my screen and start the presentation. Okay, a few words about who I am.
Fulvio, we are not seeing your presentation. The wrong window is showing.
The wrong window, yeah. Well, we test.
We are seeing ourselves, basically.
Yeah.
Again.
Okay, let me try again. Okay. No. Sorry, we tested this before, and it worked the first time.
That's
the joy of live meeting. Okay. I believe now you are seeing the right screen.
Now we can see.
Great. So I'll be quick about who I am. My name is Fulvio Cecconi. I'm an associate professor in project management here at Politecnico di Milano. I'm also the head of the bachelor in building engineering at Politecnico. And basically, if I have to describe myself with, or better, my research with one of the 7 deadly sins, it's very much about curiosity. And now curiosity led me to investigate how AI and modern digital technology can change the way we manage construction projects. And I want to start my presentation with a little, let's say, pessimistic view, because it's what I experienced in my first AI project. And you, like when your fiancé, your man or your woman split from you, and it's not about you. Most of the time it's about you. This time in AI, it's not about you. Really, you may know everything about AI, you may know everything about project management, but unfortunately, your client does not know what you want to do. Now AI is on fashion. They want to have some AI somewhere, but they are not prepared for AI. This is a survey I made with some Italian project managers and construction company, and the survey has a lot of questions because I want to hide the two ones that I like the most. And so first I asked them, do you have project for the use of AI in your company? And 80%, mostly all of the participants of the survey said, okay, we are using AI, or our employees use their own AI, which is a huge problem in a company. But because there is this hype about AI, so everybody claim about using AI. But when you ask the most important question, do you have data collection and analysis procedures in your company? Then you see that almost nobody has procedure to collect data, and data is the source of AI. AI will not work without data. So the first thing I experienced when starting the AI project was we have no data. Or if you have data, most of the time they are wrong. Or if you are very unlucky, they are both missing and wrong. So I'll show you a little bit an experience or what we did to overcome this obstacle of having missing or wrong data. And I'll show you this not as to tell you, okay, you have to do this way, but as to tell you, I did this way and it works. But I'm happy to see if there are any way to do this. Most of the work I will show you was done by Anya Kodobashian during a PhD, which I have the privilege to supervise. And so I want to thank her publicly here for the work she did. Okay. How I don't spend any time in telling you what AI is, what machine learning is, what generative AI is. But let me point out that unfortunately, I will not talk about generative AI, which is now the hype. I'll tell you a little bit about how it doesn't work now in our sector. What we do, we have data, we process them with AI, and we have output data. And if I want to fit this in a construction management process, there is a data gathering stage where you can use AI also in the data gathering stage, but doing text mining, using computer vision or whatever. Then you set up some algorithm to make decision from the data you have, and then you can do whatever you want with the information you got from your AI algorithm. So let's first see what happens when you start an AI project in a company and you find out that there are no data. We had this project that was funded by the biggest engineering company in the world, the Italian branch of the biggest engineering company in the world. And they asked us, okay, we are doing risk management. Let's do it with AI. And when we start, we pitch, we make this sort of schema and we say, okay, this is how it's going to work. We have data from our from previous project. We have project managers to interview. We will collect data. We will understand how they work. We will set up an algorithm, a machine learning algorithm, and we will have some output from this machine learning algorithm. We found out actually that we didn't have data. It took us more than a year to collect data from their company, which was huge, which was big, the biggest one. But because this company has very poor procedures to collect data and no procedures to store data from project manager experience. So what we did, we find with three different ways. The first one was okay, let's start some deterministic models of machine learning and use them on project data we have, and we spend a lot of work to collect. Let's try another way. Let's work only with the expert opinion. So let's find a way where AI help us, but only using the opinions of the expert and not using the data of the company. And then the last way was combining both expert opinion and project data. The three ways, none of the three ways works. So we need to add a little, another step that was generating synthetic data. So we need to find a way to generate synthetic data from the data we have. The easiest way to work is with AI and with let's say no data is to use expert opinion, elicit experience, elicit your knowledge from the expert opinion. This is what we did using fuzzy logic. Probably the first application of AI in the real world. Your washing machine or your is the smart washing machine actually nothing left that nothing else that a machine that use fuzzy logic to adjust the washing cycles. So in fuzzy logic, you can easily translate something like we have a very low probability of this risk to happen. We have a very high probability of this risk to happen into fuzzy function, and then you can work with this function to try to assess the risk. And this was the first way we tried. Then we tried using the most common machine learning models like decision tree, XGBoost, logistic regression, and artificial neural networks on the project data. This didn't work, so we need, because there was not enough data, and so we try to generate some synthetic data using GANs and using adversarial network machine. And we have some result also from this part. Generating synthetic data is basically you give your data to a machine with try to learn how your data, the pattern of your data. Then this machine generates some synthetic data. Another machine, and this machine is called generator. Another machine, which is called discriminator, try to understand if a data is synthetic or real. And first, most of the time, the first generation, the discriminator will understand which are the synthetic data. So you iterate this process, and the machine, both generator and discriminator, learn to learn better and better each time, and at the end, the discriminator is no longer able to distinguish whether data is real or is synthetic, and then you can use this synthetic data. We did this, and with the synthetic data and the expert opinion, we tried the third way, which actually is called solution one, which is based on Bayesian network. Bayesian networks are part of artificial intelligence, a very old part. Actually, Bayes is the godfather of all statistics, which is the basis of AI. And basically, you build a net interviewing experts. So based on the expertise, based on expert opinion, you build a net. The structure of the net, you define the structure of the net, and then you have to define parameters, weights to connect the dots of the net, and this is mostly done using the data in an automatic way. And this is the third way we proved. Again, with only the project data, it doesn't work. We had to add synthetic data also to this solution. What we did, we have 44 projects at the beginning. We want to assess risk for 11 risk categories and 65 different kinds of risk. For each project, we have 45 project variables describing the project. Solution one, the Bayesian network, proved to be a very good solution. The model accuracy is 85%. You can think that this is quite a low accuracy, but what you have to consider is that you have to compare this 85% probability of being right with the not with the absolute true, so the 100%, but the probability of a project management to be right. So you just have to improve the average probability of being right of a project manager. And if you look at this 85% in this other word, in this other way, then 85% is a very good result. It's, or at least it was a result that our sponsor thought was very good for them. The solution 2, which you see here, we tried for each one of the risk many algorithm, from decision tree to neural network. Neural network proved to be the best way if you want to go for with machine learning algorithm, but it works on, this is the graph for one kind of risk. And it is the graph for the risk where we had more data. If you go for risk where there was very few data, very few projects, then none of this kind of algorithm works. So we have to change and the way we work. At the end, we compare the three different kind of approach, the solution we have. We found out that fuzzy logic is very conservative, because when you interview an expert, a project manager, he want to be on the safe side. And so if you use only expert opinion to build your network like we did using fuzzy logic, you will get a very conservative predictor. Deterministic model, unfortunately, did not reflect the actual situation, did not work well because there was not enough data to train the neural network, to train XGBoost. At the end, the best balance was using Bayesian network, because you combine the expert opinion in the structure of the net and the data from the project when defining the weights in the net. What happens when data is wrong? So you have many data, but these are wrong. We try to predict school renovation over budget, and we did this on a very large data set, because the New York City School Construction Authority published this data set with more than 14,000 renovation projects. And for each project, they give you 15 features. So it's a huge data set. It looks like the perfect candidate to train a neural network. And so this is why we tried this. But when you look at the data, the first thing you have to do when you have a data set is to clean the data set. And when you look at the data, you see that starting from 14,000, we clean according to some criteria we define, and we end up with something like 2,500 data. Among these 2,500 data, still there were some wrong data. And so we have to clean again a second step, and we end up with less than 2,500 records. That is to say, almost 17% of the original data set. But again, this will happen always when you work with a huge data set. The second step of any work with a data set is the exploratory data analysis. You try to see if you find out any correlation among the data. Here you see a graph of delays and over budget of the renovation cost project plot against the budget itself, or the duration, or the planned duration itself. We can try to analyze correlation better. For numerical value, you can see if there is a linear correlation among the variables, and it's something we did. The strange fact was to understand that there was no linear, but even not linear, correlation between the delay and any other feature in the dataset. So it was a very bad dataset to predict the delay, and we didn't even try to. The other things you will find out when working with data in project or construction management is that data are not only numerical. You have ordinal data, categorical data, textual data. Ordinal and categorical data is a kind of data that you can easily translate into number or into something that you can feed to a neural network. Textual data can't be fed to a neural network. So what you have to do is to translate this textual data. For example, one of the data we had was the project description, what actually has been done in the project, into something that can be fed into a neural network. And to do this, we use actually the embeddings, which is the basic of any generative model you are using now. Embeddings is a way to translate a word into a vector of numbers according to a sort of dictionary. In this dictionary, the words that their meaning are related are more close than others. For example, the king and queen will be words that have embedding very close, more than queen and man, which will be most far away, and man and woman will be closer than king and woman. So it's a sort of dictionary that place vectors close together when the word is similar or in the meaning, and place vector very distant if the meanings is different. And it's a kind of tool that is used in any generative AI, in natural language processing, and in image and video understanding, and so on and so forth. We use these embeddings to translate the description of the works in the project, and we end up building a neural network that basically has 6 inputs. The project geographic distance, so where the project is, the duration of the project, the budget of the project, the kind of project. Okay, it's a project type, it's a category they divide into 5 types of project. The phase name, so when the prediction was made, and then the description, which is a text, and it's embedded in a tensor. And we want to find out, with these 6 input, the over budget, which is a float. We train different kind of neural network, and at the end, we find out, as you see here, something very interesting, because on the right, on the graph on your right, you see that the over budget, the predicted over budget is quite close to the ground truth over budget. The best is the dashed gray line you see. If a point is on the dashed gray line, means that the predicted over budget is equal to the ground truth, so the actual over budget. The R squares, it's close to 0.9, which is a fantastic result for a process where man is involved. If you use it for another kind of project, maybe not, but for this kind of project, it's a quite good result. So we can predict over budget this way, with just a little bit of work on cleaning the data and understanding the data before. So now the question we all have is, okay, instead of using all this data, why don't you feed your data to a generative model, use ChatGPT, Gemini, or whatever, and see what happens? we try actually. A PhD student of us tried an experiment with GTP 4.0 and a technique called few shot learning. That means that you give some examples to the model and then you give the data and you say, okay, go on and check and predict yourself. And you see that the result are quite wrong, are far from acceptable. As I told you before, the result should be on a line that 35 degrees with a 45 degrees slope, like this one. So the results are going the other way around. So nowadays, okay, large language model will improve and so on, but nowadays they are not good to be used in a construction project without any improvement that you can do. You can have you can fine-tune the model, you can use retrieval augmented generation and so on and so forth. But now, as they are, they cannot be used. I finished my presentation. I hope to be on time.
Thank you very much,
And
dear
no,
Fulvio,
thank you,
for your
thank
great
you.
and insightful presentation. Now let's continue with Dr. Ruichuan Zhang's presentation.
Let me share my screen. Hopefully it works. So can you all see my screen?
Yes, we can see it.
That's great. Sorry everyone. My throat has some problems, but it's very grateful to have this opportunity to give this presentation today. And my topic is Human in the Loop, AI for smart and sustainable buildings. Um, I want to start again with a little bit of myself. I'm Ruichuan Zhang. I'm from Maris Lawson School of Construction, College of Engineering at Virginia Tech. So my research has two pillars. One is intelligence. So 90% or even more of my research use AI or machine learning or deep learning models to make the design, construction, operation of built environment more automated and smart. And as Dr. Cecconi mentioned in his presentation, his great presentation, data is very important. So that's why also I focus on data sensing, fusion, and analytics to prepare data for the AI solutions we are creating. Another pillar is sustainability, more specifically social and environmental sustainability. For example, the health of occupants and workers, and also accessibility of the houses and buildings. And also my research is guided and is advancing human-centered approaches, which means that we want the humans, we want the solutions, AI solutions or machine learning solutions to be developed centered on humans and serve humans. So, and my research covers different phases in the life cycle of a building. So later in the presentation, I will share with everyone some examples. So let's just briefly take a quick overview of what is AI, because a lot of time when I talk about AI, there's some misconceptions of AI. Like a lot of people, especially people from the industry, think that AI is very new, which is wrong. AI has been around for many decades. And some other people think it's magic or it's like something like alchemy, but it's not. It's the science is a field of computer science focused on solving complex problems through computational models, math models, right? Inspired by how humans perceive, learn, and reason. So here is like a map of or scope of AI, right? So we have both rule-based systems, like it has been there for many decades, many years, and machine learning. And then under machine learning, we have this traditional or statistical machine learning, and recently deep learning, and more recently, right, large language models. And GPT is one of the example of large language models, but however, it kind of represents what AI is in many people's understanding. So here is a timeline of how AI has evolved. And we started from the concept of AI by Alan Turing, then something like expert system with if-then rules, machine learning, traditional algorithms like decision trees, and then support vector machines, and deep learning because we have more powerful computers and we have more data, right? That allows the development and use of deep learning models, and then starting in 2020s, we have the GPTs, right, large language models, and other foundation models that's very huge and very powerful. And same as Dr. Ruichuan mentioned, data is very important. We know the fuel of AI is data. Without data, no machine learning algorithms will work, right? And that's where humans come in. So humans define what data means and why it's important, when to use it, and how to use the data to, let's say, to train or build AI solution, right? I always want to compare the AI to just a person, right? A student, right? So as a researcher or developer of AI, or nowadays even user of AI, let's say user of GPT, our job is to teach the AI, right? Like a teacher, we provide reference data, or sometimes we call it training data, to the machine learning model, to the AI. And then the AI can learn about the task we want them to perform, right? So this is a very simple example, right? If we want to have an image classification model that can classify different photos into different types of construction machineries or vehicles, we need to provide them some labeled images, labeled photos, right? To tell this machine learning model, hey, this is a crane, and then this is a truck. Then later it can learn the patterns or representations that can help the AI model itself to do the classification. And if we consider AI and data and human in the scope of, or in the area of buildings or built environments, um, so we have lots of data, right, related to a built environment. We have point cloud, we have 2D, 3D, or even more ND data about the project. We have sensor data we can use to monitor, for example, environment conditions, hazardous gases, so on and so forth. We can have video data, photo data, thermal data, audio data, all of these. But these are just raw data. To go from data to um, more clean, right, and tidy information, and then something that's testable, verifiable, that's knowledge, right? AI can, that's where AI can help. So typically AI has two functions. It could be predictive or forecasting. Some of the examples later I will cover we build some AI solutions to predict, for example, the perceived comfort and health level of occupants. And we use AI to analyze the accessibility features of a floor plan. And another function of AI is generative modeling, right? So it can create new solutions, new designs, new ideas. So for example, it can help us to generate like building layout, right? Or even other designs or plans. But AI's output will have to be validated, will have to be tested, right, by people, for example, professionals or occupant, right? So they make decision, and while they are making decision, they could also provide some feedback or provide some what we call annotations or labels, right, to the data. And at the same time, they can also generate new data. So that's why we say that human is in the loop and actually is the major driving force of the loop in this data, AI, and human cycle. So, and I want to talk about a few examples in my research group. The first example is accessible building design, and we all know that buildings, especially public buildings and residential buildings, have to be accessible, which means for example, it has to have enough clearance in corridors or maneuvering space for wheelchairs so that everyone can freely navigate the indoor space. So one thing we noticed that is there is a missing solution for automatically analyze whether a floor plan is accessible or not based on, for example, the standards uh, like IBC, International Building Codes, or International Residential Codes, or in the US, we have American Disability Acts, which also have specific rules or requirements about the dimensions and spatial features of a building. So what we did is we use SAM, which is segment anything model. This is by Meta. So what it does is to segment this floor plan image into different areas, right, based on the semantics or meaning, right? So we use it to segment the floor plan into rooms and doors. And then we also classify the rooms and doors into the important rooms for accessibility, which actually connects a lot of different rooms. So for example, it could be a living room, right? Or it could be a corridor, right? So and also we classify the doors into the exterior doors, right? And interior doors. And later we use rules to, that is very straightforward after we find all the rooms and all the doors and different types of rooms and doors. We calculate two things. One thing is the maneuvering space. This is the right example, right? We calculate the clearance for the wheelchair to see if it can navigate the entire space. And we also calculate the path of egress travel. So for a specific room, we calculate the distance of travel without barrier to the exterior door, the closest exterior door. But one important thing here is to use segment anything model, you have to provide some visual cues. So in this example, right, so you probably see these white dots, right? So those are some visual cues you provided to the segment anything model to help them to focus on specific areas to segment, right? But if it's humans, if it's us to add these points or provide these visual cues, it will be very time consuming. So what we did is we also added or proposed a step to automatically create these visual prompts. So here is where humans come in, right? So they provide some 3 to 5, don't have to be very many, right? A few reference floor plans and provide to our model, and then we calculate a similarity between these references plans to the target plan we want to analyze, right? And then we come up with a similarity map, and based on the similarity map, we do a simple clustering, and it end up with those, I'm not sure if you can see this, right? The red stars. So these are the cluster results and act as the visual prompts for segment anything model. to do the steps that I just described, right? So this is the first example. But sometimes we also want to create some new layouts, right? And we also want them to be accessible. In this case, we also we proposed a generative model to create these accessible layouts. We use a models that's called diffusion models. I think some of you might have heard this is the state-of-the-art vision generation model. So the idea of diffusion is we start from something that's noisy status, empty status, and then we gradually add some noises, right? And then uh, and in the end of the process, um, we have this floor plan, ground truth floor plan, right? And the model learns how to uh, add these noises and take out these noises to recover this ground truth, right? So during this process, it can learn these semantics and visual structures of the image we want them to generate. So basically, we use this diffusion model to generate building layouts. So here's one example. After it creates something based on we will provide some input like boundaries and room list. And after this diffusion model creates some layouts, and designers or users or any human users, right? They can provide their feedback to the model, use again some visual cues or visual prompts. So they can, if they think, oh, two bathrooms, they do not comply with the wheelchair clearance and room size requirements. So we need more bathrooms for, right? So they can provide some visual cues to the model, and we will provide this image with the visual cues back to the model, right? And the model is trained to also be able to recognize these visual cues, and they will regenerate to try to solve these problems, right? So this will the diffusion model will regenerate a new solution that try to solve these requirements, and also create a well, this is using rules, right, to also create a ABC model, 3D model. So I'm not gonna dive into the algorithm or model details for this. But again, I can share with everyone our papers. Um, and in the papers, you can find more details. And I have more results for these um, two models or two solutions we created. So the left one is for the first accessibility analysis example. We actually use a campus building as a case, and so you probably can't tell, it's too small, but we have offices, labs, and other public areas. And here, these two columns, we have some example rooms and their travel, passive egress travel. And here we have basically segmented or located the corridors and also calculated the clearance of the corridor. And on the right side, we have more results for the generative model, right? So giving this like what we call condition image or the boundary and the room type labels, it can automatically create some um, um, design alternatives and also the 3D models in FC. The second example I want to briefly talk about is construction site environmental analysis. In this one, because we know that on construction site, there might be some pollutants, right? Pollution. So we want to know what is the status of if there's any pollutants, and also if we can forecast in the near future the concentration of these pollutants. So this is the first part of the solution. We have this smart monitoring system, So we have these small computing devices and also connected with environmental sensors, particularly in this case, specifically, we cared about PM, particulate matter, and also camera data. So after those data are collected, and there is a machine learning model, the YOLO model, you only look once. If you do computer vision or you do research with object detection, then you probably are familiar with this model. It's the most commonly used object detection model. Um, and we fine-tune this model with construction data, specifically the construction vehicles and construction workers. And our goal is to use this model to detect some types of vehicles and workers on the site, and use this as a indicator of the level of construction activities that could generate the PM or the pollution. So, and also here is where the construction professionals can occasionally provide some annotation, right, to the image. It doesn't have to be many, just like very occasionally, they can provide some annotations, draw these boxes to circle out these vehicles or workers to help improve the accuracy of the fine-tuned YOLO model. And then with this data, we then have a machine learning model, right? So all the three data, environmental data, PM data, past PM data, and also the construction activity data based on the detected objects. We use a deep learning forecasting model. So it can predict the future PM concentrations. So here is another small test case. Again, it's collected on Virginia Tech campus, because when I joined Virginia Tech a few years ago, the heat hall, which is our department's second building, was still under construction. So we took advantage of this to collect a lot of data. And we asked our students to also do site visits or whatever to the heat hall site and learn about construction. So we used the data from heat hall and we did this quick testing. And here is the compression of of the prediction from the machine learning model we created and the real data. So for PM1 and PM2.5, the two different sizes of PMs. The last example is about occupants, right? So we know occupant feedback is very important. They can reflect occupants' perception, satisfaction, or experience of indoor environment conditions. And they can capture how they value the environment beyond the subjective sensor data. And it can be used to support more intelligent, smart, occupant-centric buildings operations. So our goal is to have some AI-based solution that can predict the occupants' feedback or predict occupants' perception of the indoor environment based on the environment data, and also very occasionally the true feedback we collected, the real feedback we collected from occupants, right? So so here are the sensors or tools we use to collect data. On the right side, we have this very commonly used environmental sensors and some online API we can use to collect outdoor data. On the left side, we use a small interface to prompt to occupants occasionally to collect their feedback, right, in 1 to 5 Likert scales about comfort and physical and mental health. And these actually act as the ground truth, as labels again, right, for this machine learning model we created for prediction, right? So the machine learning model, again, takes in this occupant feedback, takes in the indoor condition and outdoor condition, and can predict near future occupant preferred indoor conditions. So, and we did some training tricks. We first pre-trained this machine learning model on environmental data only to capture the temporal dependencies within this data. And then we fine tune using the data labeled with the occupant feedback because they're rare, right? Because we don't have so much occupant feedback. We don't have like millions of data points to train a deep learning model. So we only use the feedback to fine tune the data. But you know, the environmental data is free, is massive, is easy to obtain, right? It does not need any labels. So that's why we can use these massive data, environmental data, to pre-train the model. And these occupant preferred indoor conditions can act as control rules to help like guide the environmental control devices. I think I'm running out of time. Before I end, we have a recent initiative I want to talk about. It's AI-supported digital twin research center by Virginia Tech and Harvard and also George Mason University. And here is a snapshot of the entire team at Virginia Tech. We have a very diverse team. This center is not just focused on building construction, but building construction is a very important direction we are aiming at. And the center is to really turn our research solutions into something that can be used to solve industry real problems. If you're interested in the center too, feel free to contact me. That's my presentation. Thank you.
Thank you very much, dear Ruichuan, for your insightful and great and, of course, interesting presentation. Now we have a little bit of time, about 8 minutes, to take questions from our participants. So please feel free to ask your questions, or you can also ask the questions in chat.
Hello, can you hear me?
Yes, we can.
Yes, thank you. Thank you to both the presenters for the nice presentations. I have a question for Professor Cecconi, and it's if you are planning to apply the similar the approach that you presented or similar ones to other domains of construction. You worked on risk to a very broad concept of risks. Now, I don't know if you are planning to apply to something else, something like construction planning or cost controlling or errors during design and construction. So which are your, say, future perspectives on your work?
David, thank you very much for the question. That gave me the occasion to say that Mina Roy is attending this seminar, is a PhD I'm supervising. She's almost ending a PhD journey, and she did a fantastic job. I don't have to tell this now, but she did a fantastic job in using visual language model and LLMs for construction safety. We have a tool that basically can detect hazard in a construction site, mostly without hallucination, which that is the worst problem you may find out. And this is basically what we are already doing. I do not work on project side, so design side, it's out of my field of research. And now we have some work going on that are quite similar to what you saw in the other presentation. But for the, let's say, for the construction site, mostly now we are focused on construction safety, well-being, and productivity.
Okay, thank you. Thank you for your answer.
Thank you. There is also a question in the chat. How difficult was to train the vision model? Which open source model was used or was fine-tuned for the task? How did you avoid hallucinations?
I don't know if he's talking about the vision model. Maybe it's not for me. I don't know.
Yeah, I can
Yeah,
probably answer this. Yeah,
Yeah.
I don't know. I think there are like many pre-trained models that's op well, I think we can use, for example, for semantic segmentation, the example I've shown, you can use segment anything like SAM by Meta. And for object detection, you can use YOLO. You can find them on I think I can share my slides or something. There are links, but you can also search them on Google. It's easy to find these places. For object detection, we have YOLO and some other models. And also there is the vision transformer, VIT, which is very commonly used for as a backbone for learning the vision representations. And then how to avoid hallucinations? I think we definitely have to do validation. So what we did is, for example, if it's a generative task, we actually ask them to generate something um, uh, that's that's actually similar to the ground truths we have. Let's say if we want them to generate a residential layout, right? So we already have a residential layout data set. Like I can't remember the name of the data set, but we have 5,000 images of these layouts, and we let the model to try to generate this and compare to this ground truth data to make sure that it's not generate something crazy, right? Like that's how we validate it. Yeah.
Okay. I believe you also answered the question of how the synthetic data can be validated. Any other question?
I can take the last one. No, there is not any Italian data set for construction project. I'm sorry for that.
Is there okay? Okay, everyone. Let's see. Yeah, thank you very much for your time and for your participation in this webinar. And I would like to thank again our keynote speakers for their wonderful presentations. And I wish you all the best. Take care and have a nice time.